Namaskar everyone. I wholeheartedly welcome you all to our YouTube channel Civil Engineering Simplified yet Detailed. This is the another video in this lecture series on Geotechnical Engineering. In the previous video, we explored the different types of rock found in India. In this video, we will explore how soil forms, why it matters, and how we can protect it for the future generation. Soil is not just dirt. It is the foundation of life, held gently in our hands, full of mystery, strength, and significance. It is a living ecosystem essential for plants, animals, and humans, but it is also vulnerable and must be conserved wisely. World Soil Day is celebrated every year on 5th of December. It is dedicated to raising awareness about the importance of healthy soil and encouraging action for the sustainable management of soil resources. In 2015, the United Nations declared it the International Year of Soil, placing soil health at the heart of global sustainability efforts. Through this initiative, the world was reminded how vital soil health is, not just for agriculture but for the civil engineering infrastructure. Before we dive deeper, let us understand one simple question: what exactly is soil? Soil is not just a dirt, it's a living, dynamic system made up of both living and non living components. Even though it forms just a thin layer on Earth's surface, it plays a huge role in supporting life. From a civil engineer's perspective, soil includes all naturally occurring loose earth material, whether organic or inorganic, that sit above the bedrock. These materials are essential for construction, agriculture, and the environment. The study of these material falls under a branch of engineering called soil mechanics. It involves the use of mechanics, hydraulics, and chemistry to understand and solve soil related problems in conservation and land use. A simple thumb rule of definition of soil is: if a material can be dug out with your hand or simple hand tools, it is considered soil. Soil is formed from the breakdown of rocks over time through a combination of physical and chemical weathering. Through natural processes like weathering, decomposition, and erosion, rock begins to crumble into finer particles. Then those particles are transported by any of the natural agency like gravity, flowing water, wind, or even ice to new places where they can settle. The environment where they land makes a big difference. After that, condition like water drainage, loading from sediments, or contamination further shape the soil's character. In simple terms, it can be stated that all soil originate from rocks directly or indirectly. The type of rock and the journey it takes influence the soil's texture, type, and engineering properties. Soil is not created overnight. It forms over hundreds, sometimes thousands of years. On an average, it takes 500 to 1000 years just to form 2.5 centimeter, that is 1 inch of topsoil. Thousands, sometimes millions of years of natural weathering, biological activity, and slow transport formation of rock takes to form deeper layer of soils. One of the process of soil formation is mechanical or physical weathering. It is the process that breaks down rock into smaller pieces, but without changing their chemical composition. That means the mineral stay the same, but the rock just get crushed or fragmented into smaller bits. The process happens through natural physical forces like flowing water, frost, and ice, temperature fluctuation, wind, or even glaciers. These forces chip away at rock over time, causing disintegration, and the result is usually coarse grained soil like gravel or sand. Common processes that cause mechanical weathering include exfoliation, where rock layers peel away, loading, unloading, erosion, and cycles of freezing and thawing, which expand, cracks, and breaks rock apart. Another major process behind soil formation is chemical weathering. Chemical weathering changes the actual chemical structure of the rock. Through reaction with water, oxygen, acids, and even living organisms, the minerals in the parent rock are transformed into entirely new substance. These processes are part of hydration, oxidation, and carbonation. The key players in chemical weathering. Over time, these reactions break down through rock into softer materials like clays and silt, which are crucial component of fertile soil. Once rock break down through weathering, the resulting material might stay right where they are or be moved elsewhere by natural forces like water, wind, gravity, ice, and any other natural agency. If the weathered materials remains at the original location where they formed, we call this residual soil. It sits directly over its parent rock and has not traveled far. But if the material is moved from its place of origin by wind, water, glacier, or any other natural forces and then redeposited elsewhere, it is called transported soil. Fine particles like silt and clay are found near the surface, while coarser grains and even rock fragments appear deeper down. Soil formation is not just about breaking rocks, it is also about movement and deposition. And that's how landscapes are shaped from mountain slopes to river valleys. Transported soil can be grouped into several categories depending on the mode of transport and where they get deposited. When the gravity works as a transporting force, it leads to colluvial deposit. These are soils that slide or fall down slopes, often during landslide. Talus or loose rock debris at the base of cliffs is an example of colluvial soil. Glacial soils are moved and deposited by glaciers. This soil is coarser and mixed. Eskers, drumlins, and glacial till are common in region. Alluvial soils are carried by running water and deposited along river banks and flood plains. These are some of the most fertile soil in the world. The soil settled in quiet lakes where the water is still is termed as lacustrine soil. Marine soils are deposited in sea or ocean, often rich in clay and silt. When the soil moved by wind, creating sand dunes and loose deposit, especially in arid region, are classified as aeolian soil. Soil is made up of particles of various sizes, each with unique property and uses. Boulders are the largest fragments having size over 300 millimeters. They are essential big chunks of rock. The rock fragmented falls in the range of 80 millimeter to 300 millimeter is classified as cobbles. The particle size range of gravel is from 4.75 millimeter to 80 millimeter, and it is often used in construction and drainage. In soil mechanics, sand are termed as coarse-grained soil. They range from 75 micron to 4.75 millimeter and can be rounded, angular or subangular in shape. These are cohesionless particles, meaning they don't stick each other easily. Silt and clay are collectively classified as fine-grained soil. Silt particles range from 2 micron to 75 micron, where clay, the finest of all, having particle size lesser than 2 micron. Based on interparticle attraction, soil is classified into two categories: cohesionless soil and cohesive soil. This classification is fundamental in geotechnical engineering as it determines how soil behaves under various conditions, including seismic loading, foundation design, and ground improvement. Interparticle attraction refers to the forces that hold soil particles together. Cohesionless soil lacks significant interparticle attraction or cohesion. Gravel and sand falls under the category of cohesionless soil. Cohesive soils have significant interparticle attraction. Particles are stick together, allowing the soil to retain shape when molded, as seen with the clay lump in the hand. Silt and clay exhibit cohesion. The classification based on interparticle attraction help engineers select appropriate soil types for construction project. Cohesionless soil like sand and gravel are ideal for free draining application, while cohesive soil like silt and clay are suited for projects requiring safe retention with proper moisture control. Loess, loam, marl, bentonite, turf, peat, humus, muck are a few examples of the types of soil we deal with as a geotechnical engineer. Soil is one of the most precious natural resources on earth, and yet it is often taken for granted. From agriculture point of view, without healthy soil, we can't grow food, support ecosystem or maintain clean water. That is why soil conservation is not just important, it is essential. Farmers around the world use a smart, sustainable techniques to protect and preserve soil. A strip cropping, contour plowing, no-till farming, and crop rotation are few key methods to conserve the soil. One of the most effective soil conservation techniques used by farmers is a strip cropping. A strip cropping involves planting different crops in alternating strips across a slope or a field. These strips act like natural barriers, helping slow down water runoff and prevent soil erosion. Some strips of plant absorbs water and minerals more efficiently than others, improving nutrient uptake and water management. When water flow across the field, the stronger strips slow it down, acting like a small dams. This prevents the weaker or more vulnerable soil from being washed away, especially in areas where minerals are lacking and the structure is loose. Over time, this method helps maintain the health and fertility of the soil, allowing the land to stay productive for much longer. Another powerful method of soil conservation is contour plowing, also known as contour farming. This technique involves plowing along the natural curves and contours of a sloping field rather than in a straight lines. It is especially useful in hilly or mountainous area where erosion is a serious threat. It helps to keep topsoil in place, which is essential for healthy crop growth. Contour farming improves irrigation efficiency and helps conserve water, especially during dry season. No-till farming is the practice of growing crops or pasture without disturbing the soil through tillage. Instead of preparing the soil, seeds are directly planted into crop residue from previous season. This was also known as zero tillage plus crop residue management. Farmers use a specialized equipment like happy seeder or turbo seeder to plant seeds without disturbing the soil. No-till farming is a smart, eco-friendly method that improves long-term soil fertility, reduces input cost, and supports climate resilient agriculture. The concept of crop rotation is a key method in sustainable agriculture and soil conservation. Crop rotation is the practice of changing the type of crops grown in the same area across different seasons or years, instead of planting the same crop repeatedly. Before we dive into the world of geotechnical engineering, let me ask you a simple question. Who is nature's first geotechnical engineer? Any guesses? Think about what in nature has been anchoring the soil, preventing erosion, and maintaining slope stability long before we started building retaining walls or using soil nails. Yes, it's a plant. Plants are the world's first geotechnical engineer. As their roots grow deep into the soil, they hold it tightly together, reducing erosion, improving soil strength, and maintaining the integrity of slopes and embankments. So, the next time you see grass on a slope or trees along a river bank, remember you are looking at nature's very own engineers at work. You might be wondering how a plant becomes geotechnical engineer. To become a geotechnical engineer, one must understand soil mechanics well. But does the plant know ground improvement techniques? Does it understand the general failure equation of soil? In the next few slides, we will see how plants contribute to soil conservation and increase the soil strength. Trees and plants have learned and mastered geotechnical engineering over the millions of years of their evolution. You will be convinced after seeing the world's largest tree. This is the world's largest tree. For a better estimate, have a close look at the base girth. Look at this picture. Do not focus at the girth, but observe the thickness of the base of the tree. This is the base of the world's biggest tree. This tree is famously known as General Sherman. It is the world's largest living thing. It is located in Tulare County, California, United States of America. It is a giant ascopia of a variety of coniferous tree. The estimated age of this tree is about 2300 to 2700 years old. It means it is older than Jesus Christ. The height of this tree above the base is 83.8, or you can say approximately 84 meter, which is taller than the Statue of Liberty. The diameter at the base is about 11 meter, which is wider than Saturn V. The circumference at ground is about 31 meter. It means it would take 20 people holding hand to circle this tree. The estimated weight of this tree is 2000 tons. It means it makes 15 times heavier than adult blue whale. So these massive trees require a strong foundation system to support their weight. If suppose say a similar weight of any building or infrastructure is built, then it needs a very good foundation. But for tree, who built the foundation? The tree itself built the foundation for transferring the load of tree to the ground safely. They have been living for several hundred years. They have weathered storms, wind, snow, and all kinds of incremental weather for centuries without any failure. This would not have been possible if trees did not have smart knowledge of geotechnical engineering. Not only large trees were good in foundation, but even a small plants like vetiver enhance the strength of soil. Here it can be seen in this figure. The vetiver used in a erosion control work in a tea garden in Karnataka. So this kind of grass or vetiver is oftenly used in the slope to protect the soil from erosion. So here vetiver roots penetrate deep into the soil surface and cut through the failure envelope. Failure envelope means from where the soil fails. So the confining effect of the root strengthens the soil. Also, the vegetation obstructs the runoff, surface runoff on the slope surface and prevents soil erosion. So once the water comes through the slope, the velocity of the water is reduced due to this vetiver or due to the obstruction of the grass. So ultimately the velocity of water reduces and the erosion of soil becomes minimized. Surface runoff loses velocity with every obstruction and slope protected from soil erosion. Carl Terzaghi is widely recognized as the father of modern geotechnical engineering, laying the foundation for soil mechanics as a scientific discipline. His groundbreaking work in the early 20th century introduced the concept of effective stress, revolutionizing how engineers understand soil behavior. Through his research and publication, Tarjagi bridged theory and practice, transforming civil engineering and shaping the field we know today. So today's lectures focused on soil and its formation, providing a comprehensive overview of soil properties, types, classification, conservation techniques, and the role of plant in geotechnical engineering. We have been introduced to what constitutes soil, emphasizing its composition and importance. We have been also explored the process by which soil is created, including weathering of rocks and organic activity. Transported soil, residual soil, and classification of soil based on grain size was also discussed. We discussed method to prevent soil erosion and degradation, including strip cropping, controlled plowing, no-till farming, and crop rotation. Plant as a geotechnical engineer highlight the role of plants in stabilizing soil through root system, improving soil strength, and aiding in ground improvement, drawing a parallel to engineering principles. I hope you understood today's lecture, which underscored the interdisciplinary nature of soil science, blending agricultural practice with geotechnical engineering application, and emphasized sustainable soil management techniques. So stay tuned with us, subscribe this YouTube channel, share this video link with all your civil engineering friends. All the best. Jai Hind.